Okay, before we work example problems on finding solids of revolution, where we analyze the given problem and decide if we're going to use washers or discs or shells, decide if we're going to use the washer or disc method or the shell method, I wanted to do some more problems on, we're strictly going to find volumes of revolution using cylindrical shells, and the axis of rotation is going to be away from the origin axes, y is equal to 0 or x is equal to 0. So let's do a few more problems where we're going to find the volume of a solid of revolution, but we're going to use cylindrical shells every time. So each problem we're going to be given a set of curves, and those set of curves are there's going to be an area contained within those curves. So here here's x cubed, y is equal to x cubed, here's y is equal to 8, and here's x is equal to 0. So we want to find the volume of the solid created by rotating this area about x is equal to 3. So about x is equal to 3. Okay, and so what we're going to do is similar to the disc and washer method. So that's where we're using the traditional, the main integration technique with breaking up the solid into right cylinders. For that method or the cylindrical shell method, when we're just looking at the plane, before revolving the area about the axis, we're going to have a rectangle for both methods. We're going to start with a rectangle. And you can think about, so if we were doing the disc and washer method, then the rectangle would be oriented horizontal in this case. Why is that? Because you can think about the revolving this, when you revolve this around this x is equal to 3, you get a washer, right? And that's the idea. This is the main integration technique where you have the cross-sectional area cut across the solid. That's the function. It's the cross-sectional area at each point on the independent variable, and then times the delta independent variable, the delta x, so that this would be the delta y, and then you get that right cylinder. All right, so if we're using the shell method, then we know here that the rectangle is going to be oriented not sideways, but it's going to be up and down. The rectangles for the washer method and the cylindrical shell method are always, for any given problem, they're always going to be oppositely oriented. So for the disc and washer method, the independent variable would be the y-axis, but here then for the cylindrical shell method, the independent variable is going to be the x-axis for sure. And so if we draw an element here, the rectangle is going to be, the height of the rectangle is going to be evaluated at the center point of the interval. And what's going to happen is when you revolve this around the axis that they give us, about the axis of revolution that's given, what do you get? You get a cylindrical shell. Right? And that's what we're going to be doing an integral. So we're going to break this up into an infinite number of cylindrical shells to get the volume. So what's the volume of a cylindrical shell, of a piece of a cylindrical shell or any cylindrical shell? So if this here is r, and this is the radius of the mid, so you have the inner radius and the outer radius, the mid between the inner and outer radius, that's r here. And so, and you have a height, and this is a R2 minus R1. Well, it would be, yeah, R2 minus R1 would be that there's a thickness, and the volume of a cylindrical shell is, you do 2 pi of that mid plane, so that mid plane circumference, so that, you know, the radius that's in the middle between R2 and R1, that circumference times the height times the thickness. All right. Now the thickness is going to be given by the delta x, or the delta independent variable. We can see that. All right. So now the height of the cylindrical shell is or the height of the element here is based on the function evaluated at the independent variable. So, all right, we're going to be integrating from 0 to it looks like 2. Let's verify that. So we set these to equal x cubed is equal to 8, 2 cubed is equal to 8. So yeah, we're going to be integrating from x is equal to 0 to 2. Then we've got 2 pi. Now what's the r going to be? What is r? So we're trying to calculate the volume of one of these elements here. And then we're going to integrate from 0 to 2. So what's the r? The r is, and this is why it gets a little more difficult with when the axis of revolution isn't the, y is equal to 0, x is equal to 0. The r is this distance, right? And you might be saying, well, what about, so don't we have to get that we have to evaluate at the midpoint, right? That is true, but remember, when you take the limit as n goes to infinity, then whether or not you choose the left or right or a point of the interval to evaluate the function doesn't matter. So it doesn't matter. If you're doing an approximation, like n is equal to 30 elements, then that's why, the cylindrical shell Riemann sum is set up where you're using the function evaluated at the midpoint. But for the integral, it doesn't matter. We're just, this distance here, okay, we could just find this distance to any point we want on that interval. This rectangle will be at some x, right? As n goes to infinity, everything converges to just that one value of x. Whatever this is defined, this rectangle is defined to be at. So you're at some, when we're dealing with this rectangle, we're at some position x. Okay, so if we know that position x, right? So based on a given x that we're at for a rectangle that we're at, what is this distance? It's 3 minus x. So the r is 3 minus x, right? Because you're going to be revolving it. You see, that's the radius. 3 minus x, that's the radius of this shell here. Okay, so 3 minus x. Now, what's the height? Well, the height is where the function comes in. And here, this height it would be 8 minus this height here. And that is x cubed. So let's do... Okay, so we've got the 2 pi r and the h. What about the t? That's just the delta, the independent variable, dx. There we go. So now this integral is the infinite sum of these cylindrical shells from 0 to 2. From x is equal to 0 to x is equal to 2. So let's take out the 2 pi. So we've got 24 minus 3x cubed minus 8x plus x to the 4th. Okay, so doing the integration, we've got 24x minus 3/4 x to the 4th minus 4x squared plus 1/5 x to the 5th, evaluated from 0 to 2. So 2 pi, when you plug in 0, this all becomes 0, so we just need to evaluate this at 2. 24 times 2 is 48. 2 to the 4th is 16. 16 divided by 4 is 4. 4 times 3 is 12. 2 squared is 4. 4 times 4 is 16. 2 to the 5th is 32. Okay. 48 minus 12 is 36. 36 minus 16 is 20. So 20 plus 32 over 5. 20 times 5 is 100. So 132 over 5. 132 times 2 is 264. And that is the volume. Okay, so the area contained within these two curves, here's y is equal to 3, here's 4x minus x squared. So this area revolved around x is equal to 1, which is here. Okay, so this area revolved around x is equal to 1. What's the volume? What's the volume of that solid? Okay, so when we're thinking about shells, it's not going to be horizontal. That would be a washer. It's going to be vertical rectangles. So let's draw an element here. We want to put the function at the midplane of the element. So like that. There is an element. Well, it's not an element, it's a rectangle. The element, we have to draw it out. There's the cross-section of an element. Okay. So, okay, again, the volume is 2 of a cylindrical shell, 2 pi r h t. All right. So, okay, we're going to be, so the x is going to be the independent variable we can see, right? That's the thickness here is delta x. So we're going to be integrating from, looks like 1 to 3. Let's verify that. So 4x minus x squared is equal to 3. So x squared minus 4x plus 3 is equal to 0. So x 3, 1, x is equal to 1, and x is equal to 3. Yeah, so we're integrating from a is equal to 1 to b is equal to 3. So from 1 to 3, so we've got 2 pi. Now what is the r for each element, right? So this is the r. So what is that distance in relation to the coordinate system? So if we're here, right, we're at this point. For this element, we're here. We're at this is x, that we're at x. This is x. So then this distance here would be x minus whatever this is. That's x minus 1. So r is x minus 1. All right, what is h? What is this distance? It's the function evaluated, to get this height of the red curve, which is, so 4x minus x squared, and then minus whatever this is, this height, that's x is equal to 3. Okay, so we've almost done, then now we just need dx. Delta x, and so there you go. We're doing the infinite sum of this is the volume. You can think about this is the volume of one of these elements if we've broken it up into an infinite number of these elements. We've broken this up into an infinite number of these cylindrical shell elements. So now we want to sum these from 1 to 3. So let's take out the 2 pi. Okay. You've got 4x squared minus x cubed minus 3x minus 4x plus x squared plus 3 dx. Okay, so we've got minus x cubed. All right. 4x squared plus x squared is 5x squared. Minus 3x minus 4x is minus 7x. plus 3. Okay, now let's do the integration. So minus 1/4 x to the 4th plus 5/3 x cubed minus 7/2 x squared plus 3x going from 1 to 3. Okay, so 2 pi. Now let's plug in 3. So 3 to the 4th is what? $81, okay. Minus 81 divided by 4 plus 3 cubed divided by 3 is 3 squared. 3 squared is 9. 9 times 5 is 45. 3 squared is 9. 9 times 7 is 63. 63 divided by 2 plus 9. Okay. Minus 1/4 plus 5/3 minus 7/2 plus 3. Okay. Minus 81 divided by 4 plus 45 minus 63 divided by 2 plus 9 is 9/4 minus 1/4 plus 5/3 minus 7/2 plus 3 is 11/12. Okay, so 2 pi times, let's see, 9/4 minus 11/12 is 4/3. So 8/3 pi. All right, so here we've got x is equal to 2y squared, y is greater than or equal to 0, and x is equal to 2. So here is x is equal to 2y squared, here is x is equal to 2, and then the shaded in purple is y is greater than or equal to 0, and we want to revolve this around y is equal to 2. And so what they're talking about here is, this is kind of confusing, but by saying this y is greater than or equal to 0, they're in effect putting a line here. And so now we this is the region. You say, it's kind of confusing. I don't know why they didn't just say x is, or y is equal to 0, but okay, so we want to revolve this area about y is equal to 2. Okay, now to do this, we're going to, we wouldn't do this as this kind of rectangle. That would be a washer. If you revolve that, you get a washer. So we're using shells here. So we're going to be doing, the rectangle will be like that, where you can see that it's a delta y. So we're going to have y as the independent variable. So, all right, so the volume of a shell is 2 pi r ht. So with y as the independent variable, we're going to be integrating from 0 to, it looks like 1. Let's verify this. So when does 2y squared equal x is equal to 2? You want to verify, like you can visually see that it's probably, this is when y is equal to 1, but that's just a visual estimate. You want to do the math and get the exact answer. So dividing both sides by 2, you get y squared is equal to 1. Y is equal to plus or minus 1, but we're not concerned with this. right? When x is equal to 2, y is equal to either here or here, but we don't care about this. So yeah, we're going from a is equal to 0 to b is equal to 1. Y is equal to 0 to y is equal to 1. Okay, so and you know, yeah, so when you revolve this, right, when you revolve this around y is equal to 2, you get a cylindrical shell, right? So what is all right, so we're integrating from 0 to 1, 2 pi. What is, for any, we're going along the y-axis, so for any position y, so we're going to be integrating from 0 to 1, because we're going to have, for each y position, we're going to have a shell, right? We'll have a shell here for this y position, etc. So if we're at a certain y position, if we're here, then what's well, let's do this shell here. If we're at this y position here, okay, what is the radius of the shell? You know, I didn't draw this to, you know, this is not, I should have gone further out, right? It's supposed to be symmetrical about this. This should be further out. What's the radius? It's this distance. This is r. Well, what is that distance? That's going to be 2 minus y. 2 minus y. All right. What's the height? What is this distance? The height of this, that distance. It's going to be, so 2, x is equal, so 2 minus this distance. What is this distance? Well, you plug in y to get this x value. That's, so you plug in, it's 2y squared, right? That's what this, x is equal to 2y squared, that's what this is. You plug in the value of y, you get this horizontal x value. Okay, so we're not done. What about the t here? That's dy. Okay, so we've got 4 minus 4y squared minus 2y plus 2y cubed dy. Okay, so let's do this integral. 4y minus 4/3 y cubed minus y squared plus 1/2 y to the 4th, evaluated from 0 to 1. Okay, so when you plug in 0, this all goes away, so we just need to evaluate this at 1. Okay, so 4 minus 4/3 minus 1 plus 1/2. So this is 4 minus 1 is 3. 3 plus 1/2 is 3.5, which is 7/2 minus 4/3. So 7/2 minus 4/3 is, common denominator is 6. 3/3 times 7/2 is 21/6. And then 2/2 times 4/3 is 8/6. 21 minus 8 is 13. So 13/3 pi. Okay, so now in the next video, we're going to work a prop. We're going to find the volume of solids of revolution, and we're going to analyze the problem and decide if we're going to use the disc washer method or the cylindrical shell method.